Okay, good evening, everyone. Good evening, everyone. It's a great pleasure for me to introduce our next speaker, Stephen Murdoch. He's going to give us a brief description of how the transition from magnetic credit cards to modern smart card-based was perceived as an increase in security, but actually it gives way to new fraud attempts and to new attack vectors. And here's Steve Murdoch. Enjoy the talk.
Okay. Hello, everyone. Can you hear me okay? Roughly. Oh, no. Okay, that's better. Okay, so I'm going to describe some work that me and my colleague Saar Drimer have been doing at Cambridge on the chip and pin system. That's the smart card payment system that's used in the UK. So a rough outline of my talk is I'll first give some background to the chip and pin system and then explain what a relay attack is. Then I'll give you a video of where we demonstrated this, and then I will discuss one fix against relay attacks, which is a distance bounding protocol, and I'll give a demonstration of this. So, chip and pin is the UK implementation of EMV. EMV is a smart card payment system, and it's used in pretty much all countries apart from North America. It's now being deployed in Canada, and it's been fully deployed across most of Europe. And since 2006, February 2006, it's been mandatory in the UK. I mentioned in the slide that the banks make very grand claims of security. It was said to be a safer way to pay, but when you speak to the banks as a victim of fraud, then they'll say that there's no way to clone a chip and pin card. What I'm going to show is that you don't need to clone it in order to attack the system. So it uses PIN at point of sale. So I've done this in Germany to get my hotel. When you put your card into the slot, it asks you for your PIN. It checks the PIN is correct, and if it is, you can go ahead. The card itself can do cryptography. In the UK, it can only do triple DES, which is called static data authentication. In Germany, there's another system called dynamic data authentication, where it can do RSA as well, but the relay attack applies just as well to both types. And relay attacks is one type of vulnerability, but in the later section of the presentation, I'll describe some others. So here's roughly how a smart card EMV transaction works. So firstly, the cardholder plugs their card over here into the terminal that's controlled by the merchant. The card has a key on it, K, a cryptographic key, and the bank over here knows what that key is. So the customer puts the card in and types the PIN into the terminal. The card checks whether the PIN is correct, and if it is, it sends a cryptogram, shown here, to the terminal, and then from the terminal, this is sent to the bank. The bank will check whether this is the real card being used, and it can do this because it shares the key, and if it does, it allows the transaction to go ahead. This is called online authorization because the merchant's terminal needs to talk to the bank in real time. So it will either use the internet or, more often, ISDN in order to connect to the bank. The merchant account is the type of bank account that you need to do this. But if for some reason you can't connect, for example, you don't have a phone line or it's engaged at this moment, then you can also do offline authorization. This is where the merchant's terminal checks whether the card appears real and there's a public key certificate, which allows it to do that. But because the merchant doesn't know this key, K, it can't confirm whether whether the real card has not been cloned. Whereas in the more secure system, dynamic data authentication, which isn't used in the UK, you can also do a public key computation with the card, and it will confirm whether the card hasn't been cloned. So let's suppose I'll take an analogy of, say, I want to beat a chess grandmaster at chess, or even draw with him. Let's now suppose that I barely know the rules of chess, but I'm not a very good player. There's absolutely no way I'll be able to beat a chess grandmaster. But how am I going to do this? Well, one thing is I challenge 2 chess grandmasters and play a tournament against them simultaneously. And when my opponent makes one move, I look at that and then make the exact same move to my other chess grandmaster opponent. This means that, at worst, I'm going to draw. I'm certainly going to play a very good game, and I'll probably win against at least one of them. Now, you can do the same with credit cards, because the card knows a secret that I've got no way of cloning, but I can ask it questions, just like a terminal can ask it questions. And then I get the answer, and once I've got the answer, I simply pass it on. I get the answer from a real card, and then I pass that on to a real terminal. And because the card doesn't have any display on it, the card holder who's sitting in front of it doesn't know how much money they're authorizing to spend. So you might think you're paying in a shop for a €5 bottle of beer, but at the same time, the accomplice of that shopkeeper is in a diamond store buying a $5,000 diamond, and you've got no way of seeing this. So we mentioned this in a paper a few years ago, that this was possible, and the bank's general response, actually to everything that we seem to do at Cambridge, is that the Cambridge people are very clever, and we find it very amusing, but this is laboratory conditions, and it's not actually going to work in the real world. So we wanted to see, will it work in the real world? When I was at the previous CCC, I might have shown you a video of a chip and pin terminal playing Tetris. Now, this was fun. We released it in Christmas days, something silly. It went on to Boing Boing and a few other tech websites. But the real reason we're doing this is to demonstrate the relay attack. But I'll show you the video of the chip and pin terminal playing Tetris. I hope. Okay. So I thought when we did this that if the voting machines can play chess, then at least my one can play Tetris. So this is a real chip and pin terminal. We ripped out most of the insides. These ones have a proprietary microprocessor on them. So rather than reverse engineering that, we put in our own hardware. It's an off-the-shelf card reader, so it reads the card. If you put a real card into it, it will say your name because the card has your details on it, and it plays a reasonable game of Tetris. So now we've got one of these, we can see, can we actually do a relay attack in practice? And I'll show you a quick video, it's about 6 minutes, from the BBC Watchdog programme, who filmed us doing this for real, in a real shop on a Cambridge High Street. Hopefully sound will work.
Hello, good to see you. We're live from the office where tonight, as you may have seen on the news, Watchdog is asking if Britain's banks are playing fair when someone steals money from your account.
Unless it was your fault, the bank's own rules say that they should give you the money back. But lots of you have told us that that's not always what happens. They could even blame you. And it's all to do with this, your chip and pin card.
Now, when these came in last year, everyone says it could be cracked. Well, wait till you see what we've been able to do on an ordinary high street. That's coming up later.
If someone stole your bank card and used it to withdraw money from your account before you'd had a chance to realise it was gone, you'd presume you're entitled to get your money back, wouldn't you?
Imagine if the bank said no. Imagine if they told you it was your fault, that you'd been negligent, that the only way someone could take your money is if you'd given them your PIN number. This is a chip and pin card. The UK switched them a year ago. They were supposed to make our transactions more secure. The irony is that when things do go wrong, It now looks like we're less protected than we were before.
In the days when proving that you'd authorised a transaction involved producing a piece of paper with your signature on, it was relatively easy for everyone to know whether you'd authorised it or not. The banks have introduced a system with a PIN which simply takes that clear proof away.
In the past, if your signature had been forged, by law the banks had to pay out. But there is no law to cover PIN transactions. The only thing protecting the consumer is the banking code, a voluntary code of practice that all banks are signed up to.
The banking code says it's up to the banks to prove that you've been negligent. If they can't, then they have to give you your money back. But that's not what's been happening. Since chip and PIN came in, it's up to you to prove that you've done nothing wrong. The reason the banks take such a hard line is because they assume chip and PIN is unbreakable. But the banks are wrong. We know of at least one way that chip and PIN can be vulnerable.
These Cambridge University researchers, Stephen and Saar, are about to show us that they can access chip and PIN information from somebody else's card. Here's the victim, one of our team about to pay for his lunch. It's going to prove very expensive. In a bookshop a few doors down the road, Stephen is waiting to hijack his chip and PIN details. He'll be using a fake card linked to a computer hidden in this backpack. Stephen has an accomplice. Saar is working in the cafe where he's tampered with the chip and PIN machine. Instead of sending information to the bank, card details will be sent wirelessly to the computer in the backpack instead.
Got a customer.
Ready to go, Saar tips off Stephen in the bookshop, who's in position to make his own purchase. It's more expensive, but he doesn't plan to use his own money. The customer in the cafe keys in his PIN to pay his £5 bill. As he does so, his chip and PIN details are automatically sent to Stephen in the bookshop.
PIN is 8046.
He enters the hijacked PIN to buy his books. It's all gone through. Both the chip and the PIN have been read by the terminal in the bookshop. The victim in the cafe thinks he spent £5. In fact, his card has been charged £50, but he won't be able to prove he didn't spend it. If chip and PIN is not 100% secure, then the bank should not be turning down compensation claims from its customers on the basis that the system cannot be beaten.
It seems that when a customer rejects a transaction, the bank's first response is really quite cursory. It looks to see if the PIN was used, and if it was, it says it must be the customer's fault, without considering any of the other possibilities, and I think that is quite monstrous.
You need to have someone who is working for the merchant. That's true. And there have been plenty of frauds where that's actually happened. The common scenario is not where the owner works, but where it's a member of the temporary staff. So, for example, a waiter could do this. And I'll show a photo later on of another case where the merchant is participating in the fraud. So could you, it's hard to hear, could you speak a bit louder or maybe get a microphone?
If you use a CVT 700, which is commonly used at gas stations or stuff like that. If you use a CVT 700, ZVT 700, into the microphone, yeah, okay. If you use a CVT 700, or in German, ZVT 700, you don't even need a PIN number because you can just put in the EC card and deposit something.
Yeah, so there's lots of different ways of doing this. In my case, when we did the demo, we took the safe option, which is where we used a voice synthesizer. It's Festival, if you've used it, which reads the PIN as it's typed in, and then it sends it over Bluetooth. But in fact, all the terminal does is it sends the PIN from the terminal to the card. So it could be that the fraudster could type in any random PIN, but then when the PIN is passed to the real card in the fraudster's terminal, it just overwrites it with a real one. But we did this one just in case the terminal sends the PIN to the bank. So to explain what you just saw there, here's the scenario. On the left-hand side, you've got Alice, who's the innocent victim, and who knows the right PIN and has the real card. And on the right-hand side, you have Dave, who is a legitimate merchant selling, in this case, the bookshop. And he has a customer coming in who wants to buy a £50 book. But actually what's happening is there's Bob and Carol, the two evil participants. And Bob has this fake chip and PIN terminal, and that says, in the case of the video, do you wish to pay for a £5 cup of coffee? It then reads the details off the card and sends it to the laptop, and then we used 802.11b wireless to send it to the other laptop in the backpack in the other shop. In this case, the two shops were one door away from each other, and that worked pretty well. But you could just as easily do this with GPRS or GSM and do it at the other side of the world. The laptop then sends the red card details to a fake card, which has a wire coming off it, and plugs this into Dave's terminal. And each time Dave's terminal asks the card to prove itself, it just passes a message onto Alice's card and then sends the response back again. So from Dave's perspective, the customer has come in with the real card, he knows the right PIN, but the legitimate cardholder won't find out what's happened until she gets the bill. So here's the equipment that we used. On the left-hand side, you can see the chip and PIN terminal that we tampered with. The device in here is an FPGA, and we use this to control the screen and the keypad. There's another off-the-shelf smart card reader, which is used for getting the data off the card, and you can see the front view of it down here. So apart from where we've covered up the manufacturer's logo, the terminal looks just like normal. On top, here's another FPGA, also from Xilinx, and all this does is emulates a card. So the smart card protocol is quite close to RS-232, but not exactly. So the FPGA handles all the timing, and then this little board here handles the voltage, because this is a 3.3 volt board, and the smart card protocol is normally 5 volts. And up here is a real credit card, but we've soldered lines onto the back of the chip contacts and removed the real chip from this. And then we've got a short wire that you can see going up my sleeve in order to pay for it. It might seem as if going into a shop with a card on a wire is quite suspicious, but actually when I tried this, it really wasn't a problem, because firstly, merchants are trained not to look at the chip and PIN terminal when you're typing in the PIN. And also it's recommended by the banks that you cover up the keypad when you're typing in the PIN. And it turns out that if I did that, the merchant wouldn't be able to see the wire coming off. So this is the problem. What can be done against it? Well, one thing is to make terminals tamper resistant. They already are. This is that if you open up a real chip and PIN terminal, it will wipe all the keys that it stores. But this actually isn't a problem, because all we do is rip out the existing circuit boards and put in our own. We never want this terminal to talk to the banks again. The fact that it doesn't know any keys isn't really a problem. And even if we did have to tamper it a little bit, cardholders aren't trained to tell the difference between a real terminal and a fake terminal. There's almost 300 approved chip and PIN terminal types in the UK. And I've seen plenty of chip and PIN terminals where the cover is broken and there's duct tape holding it together. I even saw one where all the tamper-resistant seals were broken on the back. Now, probably it wasn't trying to defraud me, it was just the engineer didn't have the right seals when he was cleaning up the terminal. One thing the merchant can do is physically examine the smart card and check whether it's got wires coming off it or if it looks a bit suspicious. But that's not much of a problem, because you can use RFID card in order.
Excuse me?
Yes?
Just here, over here, on your right side.
Yep, hello.
All right, I got one question. You have a complete in the store. So about the timing, how time critical is it? Because the victim has to put the card into the fake reader, and at the same moment, your complice in the other store or wherever has to put it into the real card reader, or?
Not exactly the same moment.
Maybe not exactly, but it should be about seconds, right?
You can actually extend it longer. The only requirement is that the real card is in the fake terminal during the fake transaction, during the transaction. So what could happen is that I go and buy my diamonds, and then I've got my Bluetooth headset, and then it waits until the card's been plugged in, and then it sends a message saying, now plug in your card. And if you're buying something like a diamond, then the shop assistant will be very tolerant about you trying to make up your mind whether you're going to do this. Another thing you can do is a smart card can tell the terminal to wait. So the smart card, the terminal asks the fake card a question. It doesn't know the answer because the real one hasn't been plugged in. So it just sends a response code saying, please call me again in 3 seconds, and then it can do this indefinitely.
So did I understand it right that it's just limited to, the time is just limited to the victim, how long he is willing to put his card or to leave his card in the terminal?
Yeah, that's only the limitation.
Would be a couple of minutes in the best case?
Yes.
Okay.
So if you saw from the video, when the customer plugged into their card, the terminal said dialing, and it's not actually doing that,
All
that's
right.
just stalling.
Got it. Thank you.
Thanks. Yes, and you just need to tell the customer that the card is, the telephone lines have broken and it's going to take a little while. I've been using legitimate transactions where it's 10 or 20 seconds, and that's more than enough to not cause the legitimate merchant to be suspicious. So another thing to do is that you could, the merchant could make sure that the numbers embossed on the card presented by the fraudster actually match the ones on the receipt. And in the demo that we gave, they wouldn't, because we used one of our friends' card for making the fake, but the real card, which was plugged in and is going to talk to the terminal, is going to be different. Now, this is quite inconvenient for merchants to do, and they're probably not going to do it. But even if they did, all the fraudster has to do is target repeat customers. So you come in one day, you pay, and then they record your card detail, and then overnight they make a fake card with the contacts coming off with the same card number. So a final option is to impose some timing constraints. Make sure that the real card, the card presented, responds within a certain time period. Now this is a good start because no information can travel faster than the speed of light. And if you can somehow measure the distance between the real terminal and the real card, if this is more than a few centimeters, then you know that something's wrong. So we looked at what happens with the real existing smart card protocol and what timing tolerances are there. Well, one we tried had a 3-second round-trip delay, which is huge. And at the speed of light, you can go 11 times around the Earth to the Moon and back. You can't quite get to Mars, so Martian smart cards are safe. And it's not even possible with the existing smart card protocol to reduce the timing requirements to a sufficiently low level that this type of attack doesn't work. Because smart cards are really slow. They're something like 9,600 BPS. And transactions are quite long. They're a few hundred bytes. So if you just slow the card down or speed it up by a few percent, then you can get quite a significant distance advantage. So the fix to this is to use the distance bounding protocol. And here, you send 1-bit challenges and get 1-bit responses. And because those are very short and you send them very fast, you get much, much better performance and are able to make a much more accurate estimation of the distance. So here's roughly the protocol. The verifier, in this case the terminal, sends a single-bit challenge to the prover, in this case the card. And because the bank and the card know this key, the response that comes back can only be given by the real card. So even in the case of a relay attack, the right data will come back, but it will just be too slow. So if Matt could come up and give me a hand, I'm going to try to do a demonstration of how this protocol can work. So, never tried this before, never been rehearsed, so we'll see how it goes. So what Matt has are 2 tubes of tennis balls, and inside of these are green and orange balls. These represent bits. And what I'm going to do is I'm going to hold up a flag for what tube I want the contents of, and what will happen is Matt will take the one out of the tube I asked for and give that to me, and then he also takes the ball out of the other tube and then throws that away. So I'll show why this is important later. So firstly, I'll hold up the orange flag, and that. Thanks. And Matt will take the one out of there. Here. And I got a green one out of there, as shown on the screen. So now hold up the green one. Thank you. And now I've got an orange one. And finally, I'll hold the orange one up. And I got the green one out. So because I got the answer I expected, I know that Matt had access to the real tennis tubes. And this is roughly how the protocol works. If Matt was an imposter, thanks for your help, Matt. If Matt was an imposter, he wouldn't know which colour of ball to throw at me. And I can time how long it took for me holding up my flag to when I received that, and then know how far Matt was away from me. If, on the other hand, the real Matt was hiding in the hack centre and it was imposter standing in front, then the imposter would have to run down to the hack centre, hold up another flag, and then get the right answer, and then run all the way back and hand it over to me. And you can do the same thing with electric current, and you can actually get very good distance bounds. At worst, the implementation we gave, you could work out whether someone was within about 7 meters. In practice, it would probably be closer to centimeters. So here's the protocol, in same thing as before, but now in more cryptographic terms. This is called the Hanke-Kuhn protocol, after Gerhard Hanke and Markus Kuhn, who developed it. And this was originally used for wireless devices like MyFair to work out how far the real card is away from the real reader. So the first step is the terminal sends a nonce to the card, and the card sends a nonce back to the terminal. That's the step up here. Nonce stands for number used once, and this allows the card, this makes sure that you're not replaying a previous transaction because the nonces are going to change. And then, using the key that the real card and the real terminal share, they generate a new random number, and that represents the contents of the tennis ball tubes. And it takes this random number, splits it in two, and puts one into shift register 0, the green one, and puts the rest into shift register 1, the orange one. And the verifier does the same thing, because he knows what random number is going to be generated. And then the high-speed part of the protocol is that the verifier sends a single-bit challenge. That was the flag I was holding up. And then based on that challenge, you either choose the top or bottom shift register. You take the bit off the shift register and send that one back. And the verifier can know whether this is correct. And just like Matt threw one of the balls away, the other one is thrown away. I'll show you why that's important. And then once all the bits have been collected, these can be now verified, and the verifier checks that all the bits came promptly, so make sure that the card isn't too far away, and then sends it off to the bank to make sure the bits were correct. So let's see what attacks are possible if you want to try to defraud that system. Well, firstly, if I was talking to an imposter, they could just guess bits at random. And they will get half of those right. And when we're only doing 3 bits, then that's not very good. But in practice, you would do at least 64 bits, and then that significantly reduces the chance. The other thing that the attacker can do is go to the real challenger, the real card, and then ask for all ones or all zeros. Just guess the challenges, and then see what the answer comes back. And with that answer, when the real transaction happens later on, when I hold up one of the flags, if it guessed the flag right, it can give me that back with 50% probability. But even if it guesses wrong, then it can still send me back a random one, and then those will be then that will be right half of the time. So when you combine those two attacks, then you get 3/4 of, there's a 75% chance for every bit that the attacker guesses right. And then once you do this 64 times, then you get 1 in 2 to the 26, which is something like 1 in 64 million. So it's very hard to defeat that protocol using this. So another thing the attacker can do is somehow trick the other participant into showing both of the bits, both of the contents of the shift register. And one way to do this is to run the protocol twice. This won't work because the nonce exchange at the beginning will make sure that the contents of the shift register will be different each time. The attacker could also try to sample the challenge early and then send back the response faster than a normal card would do. So rather than when I hold up the flag, the bit comes back, when I just start looking at one, then immediately the response comes back, and that gives a little bit of an improvement on distance, but still not very much. And a final attack is that if the attacker can get both of the bits at the same time, so the evil Matt would run down to the hack center and show both flags very fast, and then the other person will get confused and hand back both of them. But if you design the hardware carefully, then this attack won't work. So we wanted to actually build this, and here you can see the devices that we used. So on the bottom left and here is an FPGA board. We need to use FPGA here in order to get the data back fast enough. FPGAs can respond extremely fast, unlike something like a microcontroller. And the FPGA is here, and here you can see the 2 wires that we used to test. So when we ran the protocol with just a jumper sitting over the 2 wires, then you had a few centimeters distance. The protocol worked, all the bits came back correctly and on time, and the verifier was happy. But when we put these 30-centimeter coax cables, the protocol stopped working. So this shows that we can spot how far away the real card is, even if the attacker is very capable and can send back the responses at the speed of light. And up here, you can see the traces from the inside of the FPGA, and on the scope, you can see the challenges and responses coming back. I'll show you some more pictures of these later. So when you actually want to implement it on a circuit board, you get a circuit diagram like this. If you don't know circuit diagrams, don't worry, I'll explain how it works. So the first step is the challenge being sent. This is where the flag is being held up. So the verifier, shown in green here, wakes up and then drives the I/O line. There's only a single input-output line between the 2 devices. And then the challenge is seen on the wire. Now, this is then delayed very slightly as it travels over the wire, and then the prover, the card, sees a slightly delayed version of this. Now the prover has to work out whether a 1 or a 0 was sent. So a clock line, a separate line, sends a signal to the card to say when to sample it. So here it is being sent, and here it is slightly delayed when it's being received. When the card receives that signal, it looks at whether it's a 1 or a 0 on the I/O line. It then uses this to choose whether the top shift register or the bottom shift register is used to send the response. And once it's worked out what that is, firstly, it waits a little in order to make sure that it will not send an intermediate state and accidentally send both bits. And once it's weighted, it will put the response onto the I/O line, and then this is delayed again, and the response is seen by the verifier. And the final step is once the verifier, the terminal, is happy that the challenge has gone forward and back, it samples the I/O line. And depending on when it samples, it can decide how far away it's willing to tolerate the real card being. So if it samples over here, it means that it thinks the card is going to be very close, and if it samples over here, it thinks the card is going to be very far away. But in the middle, it will get the right answer, but if anything gets in between, then the real response will be shifted way over here, and then the wrong answer will be got, and the protocol will fail. So this diagram shows how it actually works in practice, and in theory, practice is the same as theory. In practice, it isn't. So on the top right-hand corner, you can see the full exchange. So we were doing 64 bits, and over here is just one of these challenge and response pairs. It's actually this one marked by the little black dot. So firstly, the verifier sends the challenge, which is in this case a 1. So it sends it over here, and then slightly later, the prover, the card, sees the same answer on the I/O line. And this thing here is the reflection that's coming back. And then the prover waits a little bit, and at this line, it samples whether it's a 1 or a 0. And then it decides which shift register it's going to use, the top or the bottom one. And then once it's happy it's settled, it now decides here, and it sends a signal back. And you can see that the prover, the card, sends a 0 at this point. And then a little bit later, the verifier, the terminal, sees the response coming back. And again, you've got a reflection. And from here to here is 25 nanoseconds. And in that time, light can only travel about 7.5 meters. So this means if the protocol succeeds, the verifier knows that the card is no further away than 7.5 meters. In practice, when we actually tried it, you can tell whether it's within a few tens of centimeters. And if you used dedicated hardware rather than an FPGA, you could reduce this even more. So the solution that we talked about is quite low cost. It's only a few tens of gates for the core logic, and the rest can be implemented in software. And it does require that there be changes to the EMV protocol. You need special hardware on the chip and on the terminal to do this. The reason it's cheap is because the card doesn't need to have a fast clock. They normally run at 5 megahertz at the top. It doesn't need to run any faster, so you can use the same processes they use. The terminals do have to run a bit faster because they need to decide when to sample to get the response back accurately. But terminals are already pretty sophisticated. Some of them, the Trintec one even runs Linux, so there's not very much of a problem in making these more sophisticated. And then the cards need to have a few shift registers and some control logic. And then in order for this to work offline, you would also need CDA or DDA. That's a system that's used in most of Europe, apart from the UK, where the card can do public key cryptography. But the contacts between the terminal and the card are unchanged. You still use the same lines. There's one clock line, one bidirectional I/O line, and all the electrical properties stay the same. And most importantly, the customers don't notice any difference. I'll go into some more attacks later, and it's true that criminals are probably not using this attack at the moment. That's only because there are easier attacks to carry out. Our demonstration showed you could do this with a few $100s of investment, and that's well within capabilities of criminal organizations. So although it's not so much of a problem now, as the attackers become more sophisticated and the current loopholes they're exploiting start getting closed off, then it would be worthwhile deploying this or one of the alternative solutions for defeating the relay attack. So this is what criminals are mainly using at the moment. They're not exploiting the chip because the chip is fairly hard to clone. They're just using the mag stripe because all cards issued still have the mag stripe, and this still works in most ATMs. And one thing to do, which you can see on the right-hand side, is a fraudster who, as he distracts the customer, he first of all swipes the card in the real machine and puts the real transaction through, and then with his other hand, shown over here, he's got another mag stripe reader hidden by the side of the cash desk and then swipes it through. And then with this, he gets your account number and all the information that's needed to make a fake mag stripe. And this even includes the CVV, which is a three-digit number stored on the mag stripe that ATMs use to make sure that the card is legitimate. And a fraudster can either do it by this double swipe attack, or you can intercept the card details as they're sent on the chip, because the chip contains all the same information that's on the mag stripe. And then the fraudster has to somehow get the PIN, and the way this is commonly done is simply there's a covert CCTV camera in the ceiling, and this records the PINs that are being entered. They then use the time synchronization to match up which is which, and then make a fake mag stripe card. So another way to get the details is intercept them as they're being sent from the chip to the real terminal. And cards already do this as standard. So on this laptop, this was a demonstration for ARD television in, I think, Bavaria at that point. And we put a device between the card and the terminal, which recorded all the data being sent back and forth, which included the CVV, included the name, the account number, and all the information needed to make a fake mag stripe. But more importantly, the PIN is also sent between the terminal and the card, so it can verify it correctly. And in most cases, it's not even encrypted. So this means that by intercepting one point, you can get all the data you need. If you don't need the PIN, or you can get the PIN in a different way, then you can also collect the data as it's being sent from the terminal back to the bank. In cases we've seen, that's not encrypted either. And then once you've got the details, you can create a fake card, and it doesn't have a chip, but that's okay, because some ATMs we tested in the UK will still accept cards that should have a chip, but don't. And they do this in order to help foreigners who don't have cards with chips, or just because they'd rather have your custom even though your chip's broken or their card reader's broken, or they just think something's gone a little bit wrong. Also in practice, the fraudsters don't collect the data and then use it themselves. They collect the details and then sell it off abroad. Quite often this is done in other countries because their ATMs can't even read the chips. And when we demonstrated it, that this is a UK ATM withdrawing data, withdrawing cash from an account, even though we only had the mag stripe. And you don't even need to have a proper mag stripe card. You can just use a top-up card because that's all we had handy at the time. In Germany, this is a little bit different. This is the only country, as far as I know, which uses something called the M feature, which is special encoding of the mag stripe that normal card writers can't implement. But that's not a problem because fraudsters would just steal data from Germany and then send it abroad. So I've given several examples of security problem in chip and PIN, but the banks don't really seem to admit that their system is anything less than flawless. Because if you're the victim of fraud and then you contact your bank, then often they'll just say, our system, it works, the PIN was used, so we're not going to refund you. And there's not very much legal recourse. About the best you can do is go to the Financial Ombudsman Service, who are an independent organisation, but they just seem to be saying the bank's lying back at them. So this is from a letter sent from the Financial Ombudsman to a customer who had been defrauded and tried to get money back. And what the Financial Ombudsman said, the firm, by this they mean the bank, has provided an audit trail of the transactions disputed by you. This shows the location and times of the transactions and evidence the card used was chip read. Now, does this mean that the chip was actually read? Or does this mean that the card should have had a chip, but the bank's records, which are created by millions of lines of crufty COBOL, maybe those aren't properly representing the data. So it then gets very surreal. Although you question the firm's security systems, I consider the audit trail provided is in a format utilised by several major banks and therefore can be relied upon. So what does this mean? Does this mean that it's in ASCII, and lots of banks use ASCII, so it's right? And just because several banks are using it doesn't mean it's any good. They then go on to say that although you have requested this information, security details, from the bank yourself, and I consider that it's not obliged to provide it to you, I conclude that this will not make any difference because this service has already reviewed this information. So basically they're saying that we are judge and jury, we're not going to show you the evidence necessary to clear yourself, but we found you guilty. And this feels a lot more like a kangaroo court than an independent ombudsman. And then they said, as we've already advised you, since the advent of chip and PIN, the service is not aware of any incidents where a card with a chip has been successfully cloned by fraudsters so that it could be used for them successfully in a cash machine. Well, I just gave a demonstration twice on television where this is possible. And the end, my conclusion, therefore, is that it is likely that the original card was used to carry out the transactions disputed by you, i.e. you can't get your money back. This is, as things go, a fairly good situation. We've also heard of people who have disputed a transaction and gone to the bank, and the bank said, we think you're working with a fraudster, and then sent the police on them. And there are at least 2 court cases going ahead at the moment where a victim of fraud has been charged with participating in the fraud. So in summary, I've demonstrated a few problems with chip and PIN. Some are fairly easy to fix by upgrading from the simpler static data authentication to the slightly more expensive dynamic data authentication, but others are harder. The relay attack cannot be fixed with the existing hardware. But the root cause of all these problems is that when there is fraud, the bank is able to pass the cost from rather being the fraudster or rather than them who choose to go for the insecure system onto the customer. And that's simply not fair. So what's needed is a change in culture that the banks are considered liable for fraud, and this is roughly how it is in the US, and they are liable for the losses. And this is the right thing to do because they are the only people in the position to improve the security. So if they think that relay attacks are a serious problem, then you can deploy fixes against this. Maybe it's best for them to just deploy intrusion detection systems and check whether you're making a transaction in the UK and then a few seconds later in Malaysia. But since they are the only ones with access to this information, they should be the ones who are liable for the cost of fraud. So, thanks for your attention. If you've got any questions. Anyone have questions? Yes, one couple over there. You use the microphone, please.
I have 2 questions, at least one, and depending on your answer, probably a second question. If you can switch back to the slide where you showed the nonce exchange and the 1-bit challenge response exchange.
This one?
Yes, exactly. So the nonce sent by the card, what is this actually for? What it is doing on the terminal?
The 2 nonces are combined along with the key using a cryptographic message authentication code in order to generate the contents of the shift register. The card sends a nonce because if it didn't, then a malicious verifier could ask it to do a transaction twice. So it sends one nonce, runs the protocol, gets all the ones, runs it again, and gets all the zeros. Okay. The card nonce makes sure that this can't happen.
So the nonce sent by the card at least influences the sequence of bits challenged on the real card then?
Yeah, the 2 things are combined, put in the shift register, and then that's the responses.
Okay. What's the timing constraint between the nonce exchange and the single bit challenge response scheme? Because if you have a time delay between them, of course you can put the relay in between this nonce exchange and the real 1-bit exchange, because if you know the nonces, you can simply relay that to the original card, get the responses, store it on a real card, and then just replay it to the terminal again.
So there's no timing constraints, and this is because the real terminal will send a nonce to the card, and then the real card will send the nonce back. If this, once this has happened, then the challenger, the malicious challenger, can only get half of the bits. And if it guesses wrongly, and it will guess wrongly because it can't see the challenges in time, then it won't be able to send the responses back.
Okay, thanks.
So another question slightly further back. Sorry, I can't hear you. Could you find a microphone or come closer? Okay.
Can this relay attack and this attacker C with a fake card, can it be done with a cash machine or only with in a shop?
We've never tried it, but I don't see any reason why this wouldn't work. The cash machines I've seen don't have any shield to prevent wires coming out the front.
I think it would be a little easier to get the timing right and to hide the cable, so perhaps it would be an idea for an attacker to use a cash machine.
Yes, because you don't need to worry about the timing, you don't need to even worry about someone spotting what you're up to.
I have a question, or a better explanation. So for the real-world attack, I guess it's possible to do one attack if you find a merchant who is stupid enough to take the risk, because you can hide yourself, but the merchant can't, close the shop and go away. But for a mass attack, it's, you have two problems. First of all, you must find a merchant who is stupid enough to do that mass attack. And second, the payment service provider, fraud management systems, and the payment card industry systems would track easily down that this merchant is always in charge when there was a fraudulent transaction. So in the real world, I guess there would be no mass interception because it's simply not doable. They can easily track this down, right?
The merchant doesn't need to have any records that show up that show that they were involved at the time of the transaction. So it used to be with double swipe fraud. The fraudster would swipe the real one and then swipe the card in a fake card reader. And that means that when the frauds show up, there's always that merchant involved, and then the waiter normally gets arrested. So what the waiter started doing is they gave the customer the dinner for free. So there is no legitimate transaction at that time. So the customer needs to remember where were they at that point 3 months in the past, and they weren't charged for. And I probably wouldn't remember that.
Okay, thank you.
And on the other hand, way easier, just do a refund on any card.
Sorry, what was that again?
You can reverse transactions. Just do a refund.
Yeah.
Another question concerning the PIN number on to be transmitted in clear, unencrypted. So as far as I know, in Germany, the PIN terminal only is encrypting the PIN number and comparing the result of this encryption process with the encrypted PIN number on the card. So is it different in your country?
The PIN is not encrypted in the UK because the cards there can't do public key cryptography. Okay. In Germany, the journalist for ARD interviewed Visa Germany, and they said that both types of card is being used. So if the cheaper SDA variant is used, the PIN cannot be encrypted.
Okay, thanks a lot.
Yep, there's no there.
What was the official reaction from Apex to this attack?
They said that fraudsters were not using that in the moment, which felt to me that they were missing the point, but that seemed to go down fairly well with the public.
Yeah, but that was in March, February? when you
That was in
published this, but have they reacted
That
later
was
on?
in early February.
They haven't done another reaction in the meantime.
Sorry, what was that?
They haven't done another reaction in the meantime because it's possibly showing up in the wild.
No, we haven't done anything since then, but we are continuing to work on this topic. And if you're interested, our blog, Light Blue Touch Paper, will show the most recent work that we're up to, probably in early 2009. No, 2008.
Okay, thank you.
Hi.
Hi.
Just a question. You are proposing a new protocol. Do you need to make any change to the actual?
Could you hold the microphone a bit closer?
Hello.
Yep, that's better.
You are proposing a new protocol on your presentation. Do you need to change the ISO 7613 protocol between the card and the reader, or it has to be, or you can maintain this protocol?
Most of the protocol can stay the same. So anything that's not distance critical or timing critical is exactly the same. So things like the nonce being transferred can be done using standard ISO 7816. The high-speed section has to be a different physical layer because the speeds that it's running at is far, far faster than standard smart cards can currently handle.
Yeah, so you're proposing that everyone should change their reader into a new reader?
The readers change every few years anyway. So this will be something that is rolled out slowly, and then that means that once the fraudsters are actually using this technique, they'll discover that the attack doesn't work.
Okay. Do you have any plans for studying the security of the terminals?
We've certainly published this information, and we think all the terminal and card manufacturers know about it, but we haven't heard any plans of this being deployed.
But I mean, are you studying the firmware of the firmware of these terminals in order to make attacks to these terminals, or no?
Well, are you asking about implementations of it?
No, I'm asking taking a real terminal from a shop, open the device, studying the firmware inside, and checking how to hack a terminal in order to make a transaction bigger than they should be.
Yeah. No, we haven't done that, but we already have a terminal with an FPGA in it that could implement that if we thought it was useful. The more problematic one is the card, because current smart cards can't do this distance bounding protocol, so we would need to have a separate board for that.
Okay, just one last thing. I'm from Spain, and someone copied my credit card and stole a more or less big amount of money, 2,000 euros. And then I came to the bank and say, okay, I didn't make these bots in China. I haven't also never been to China, so this is not real. And they tell me, okay, they give me all my money back without any question. And I say, oh, this is so easy. And they say, look, Visa is earning 5% of all the transactions in the world. They don't care if they don't care if someone makes a complaint. They just give the money, and the people are still believing in the system. Because if the people stop using the credit cards because they are afraid of them, they are going to lose 5% of all the transactions in the world. I just can't understand why the answer on your country from your bank.
Well, it depends on how lucky you are. When I was a victim of fraud, my bank paid me out quite promptly, but that's the same bank as the one who was not refunding this other customer. So it depends a lot on your luck, who you spoke to, also how you sound like. It seems that most of the people who we hear from who haven't been able to be refunded by their bank are women. It seems that men get a much better treatment from the banks. I haven't heard any from Spain, but I have heard ones from several other countries. So I don't think any country is particularly bad or particularly good in that respect. And we still get a few people a week who have not been refunded by their bank. And sometimes if they fight for long enough, then they get their money back. Sometimes they have to go to court, and that might work out. And sometimes they get hauled into court themselves and are accused of committing a crime. So it varies dramatically.
Hey, I had just one question, actually a clarification, I guess. In the protocol you had outlined, you were testing it using a transmission line between the transmitter and the receiver. Are you assuming that the bank is now going to have a transmission line directly to the PIN terminals now, so they can do this kind of timing?
There would need to be a fairly short connection between the logic and the terminal, which is implementing this protocol, and the card. So this might mean that rather than having a microcontroller on the terminal, you would have a little FPG or a little ASIC sitting on the same board that's actually doing the reading. But all the terminal needs to do is, even if there is a long distance, or a relatively long, say tens of centimeters, between the card reader and the thing that's doing distance bounding, it just subtracts that time away from the distance that it measures.
Okay, so the other side of the distance bounder is not at the bank. It's actually in the store?
So what the terminal does is it runs a distance bounding protocol, It collects all the bits, it makes sure that the time is right, and then it can then, at its leisure, send this off to the bank. And the bank doesn't check the timing. All the bank does is check whether the bits are correct. The timing is actually implemented by the terminal.
Got it. Okay. All right. Got it. Okay. Thanks.
Okay, if that's all the questions, then thanks very much for your attention.